Okay. Hello, everyone. Welcome to today's workshop. We'll be going over the differences between Ethereum and nil. Konstantin and I are going to be just like reviewing a couple of the things that are coming up and like progressively talking about different aspects of the nil architecture, different design decisions in the context of giving everybody like a really good primer on what the differences are. This won't be like exhaustive, but we're going to go over certain things. And like we also have Alexa who would be able to speak. But I want to encourage everybody to unmute if you have questions. The goal here is to be like very, very interactive rather than having a lecture. So yeah, let's get started. Um, uh, let's start with like Ethereum, just base definitions that allows you, yeah, it's a decentralized blockchain that allows users to create and use dApps on the internet. Fun fact, I don't know how many people know that Ethereum's first name was like the first version was Frontier. And like this, the other photo there is from like the launch when they were actually starting, when they actually kicked off the launch. I think it was somewhere in Berlin or something. Yeah. So that's what that release looked like. This isn't like an exhaustive history, but in the context of like scaling solutions, so Ethereum Frontier launches in 2015. There was the ICO sale, if you guys remember, where people were buying out of a. Oh, really? Wow, interesting. Um, yeah, so it was released to raise about 18 million through an ICO. Yay, ICO! If you remember those nice fun days. Then in about 2020, we started having like optimistic rollups, and like Arbitrum, Arbitrum and OP launched within a couple of months of each other. And these are like the first beginnings of like scaling solutions. But as you know, with all of the OP rollups is basically the 7-day finality and that whole like period. And I think to this day, honestly, none of them really have fraud proofs. And there's a whole other rabbit hole we could actually go down where that fraud proofs are actually harder to implement than um, ZKVMs, but that's a different debate. Um, then there were like numerous upgrades, but the most significant one would be like proof of stake. And proof of stake kind of opened up the door for just like different scaling solutions to find relevance. And so with proof of stake, you have like the meta of like eigenlayer and restaking and that whole narrative, but also it kind of like set the foundation for like EIP 4844, which allows us like L2s to be able to like use Ethereum as a settlement layer by being able to use the call data. And in early 2023, a couple of ZK VMs finally launched, and these were considered to be really, really like the holy grail of Ethereum. They were difficult and they were hard to wrangle. But then we had ZK Sync and Polygon and Scroll and others launching within that space of 2003. And now we have nil, and nil comes with a different uh, value proposition. But just to remind you, there's like the whole Ethereum roadmap with like the Verge, Merge, Surge, Scourge, and all those other things, and they have different like value propositions, which I'm not going to go into here, but like there's loads of different considerations, and I think currently we are basically here at EIP 4844, the implementation, and you could see optimistic rule of fraud proofs are still not yet live, but they're probably going to get there. And ZKVMs are coming with greater maturity. And yeah, there's loads more to look at, but we're still in the surge phase of this whole cycle. Um, but let's look at the proposition of ZK sharding. Um, so I'm going to have Konstantin. He and I had notes on this. So ZK sharding, the base definition, is a type of sharding architecture in which the shards are responsible for execution. And a sync committee essentially generates ZK proofs for verifying intra-shard state transitions. So when I was going back and forth with you, Konstantin, I think you had a couple of views. So how does this essentially work in a scalable fashion? So let me just speak about like the value propositions, and then we could probably go back into the definition. But like
Sure.
the whole point of zk sharding, it brings a couple of important things, which is like liquidity unification. So you could move liquidity and uh, across chains. You have a seamless execution environment. You have horizontal scaling, and we have a couple of finalization levels. But we'll go back into all these definitions. But let's start here. So zk sharding, from an architectural overview, Constantine, what does it mean to you, and what does that look like essentially?
Sure. I approach this as an engineer and from the classical systems perspective. I think if we lived in a world where all L2 solutions agreed on one approach, this is what it would likely look like. So if we lived in a world where the L2s can have the common layer for exchanging information, and they all agreed on the principles, on the designs, and on the way the code would be represented, then I guess that would be it. That would be it. So people would agree on the architecture and be done with it. The same thing as with the cloud providers. The reason why cloud providers want vertical integration is because it's just not very possible to have one cloud create databases, the other cloud create queues,
Yeah.
and the other cloud create Lambda functions without a common framework to operate things. This very quickly falls apart. There were approaches, but they all lost to the vertically integrated clouds for one reason or the other. If anyone remembers Heroku, so
Yeah.
essentially the idea is that we cannot build an efficient scalable system without at least some sort of vertical integration between the parts. This is mostly due to how the parts exchange messages. So you can think about this as a lot of simpler, smaller blockchains unified by the common layer for message exchange. That should be fast. The core problem is exactly this: the speed of message exchange and how you guarantee that the messages that one small blockchain emitted are going to be landed on the other blockchain, and the other blockchain can trust that this is exactly the message that was supposed to be emitted. And also you have this sort of expectation that the code executed in one place is the same that the code that is executed in another place. So
Yeah.
said that they share the same runtime environment, which is important for people who want to write something that works on the both legs of this equation. So for this purpose, we think that you definitely need something that approaches an L1 that works with Ethereum, because in order for your network to be fast and reliable, you need consensus. So without a consensus, just cannot work well. So you need a way to verify, at least to some degree of certainty, that the message exchange is correct, and you don't have double spending and things like that on the layer that executes things. Otherwise, you can get a lot of different failure scenarios that you have to account for, in particular with rollbacks. So in our case, because we are vertically integrated, if one side cheated and we caught it at cheating, we know that it will be consistently rolled back, and you won't see the consequences of that misbehavior reflected in another place that cannot be rolled back. So we want to have a simple, concise protocol for rolling things back, and under normal circumstances, they can proceed forward at a decent pace, with a decent level of security. Of course, by definition, if you're talking about like distributed networks, distributed systems, you have to make a trade-off somewhere. So as with many L2s, this is by decreasing the security guarantees and to some extent for some window of time, which is unavoidable. But we think that you can reach a lot better level of security that what the current networks give you by having a proper consensus. So this is just a combination of a few approaches that successful things just are doing right now.
Yeah.
ZK part is, I would say, if we are talking about ZK part, it is ideal if users would not even experience the ZK part itself. So they should just know that there is a window where after which their transactions are as probably as secure as Ethereum with high degree of certainty. So and the ZK part should be more or less hidden.
Right. That makes sense. Yeah, and I guess generally with general ZK VMs, the goal has always been to do that. Other than, I guess, ZK Sync, which is like a type 4, which requires you to make code level changes. And like type 4 general ZK VMs, I think it's an important consideration. Cool. So the takeaway there is from a scalability standpoint. So if Vitalik could go back in time and start Ethereum with the knowledge that you've gained so far, your assertion is that this is what it would look like now from a scalable for it to be efficiently scalable.
Probably, I would say that. I guess if he was in his position back then, I think he would probably have done it the same way he did, because the reason is not in the knowledge of future, is because it's pretty hard to bootstrap things to the current state, and it's just that you need a lot of prior knowledge. With prior knowledge and all information that we have right now, probably he would have chosen to do sharding, at least to some degree. I think so.
Cool.
They were considering sharding seriously for a while. It's just, I don't know, if I was running Ethereum, I probably wouldn't have risked the transition to sharding, because it changes the paradigm a lot. And as soon as you have centralization and a lot of people depending on the features of centralization, being able to execute transactions synchronously and things like that, it's very hard to break out without risking the loss of capitalization, things like that, which is obvious. I probably wouldn't risk it.
It's a real concern. Yeah. All right, cool. Anybody have any questions in the audience, or like something to say or chime in before we move on? Okay, cool. All right. So inside of our discussion, like we may look at Ethereum, but we're also going to be just doing like considerations with other Ethereum L2s. So Ethereum is now kind of like a settlement layer, and so we're not going to be just confined to that. But like, let's start by like looking into some of the different paradigms when you're looking at this here. So EOAs and wallets, basically. With nil, we essentially have smart contract wallets built in as like the de facto standard, and we have pre-built wallets that you could write your own custom smart contract wallet. From a feature standpoint, why was this an important development, and why was this considered to be central to the roadmap, Konstantin?
Well, there are a few things why we decided to go with smart contract wallets. One of them is because of the difference between external message passing and internal message passing. So we needed a way to verify that the external messages are correct, and we thought that in many cases, we already know about many cases where people are building custom wallets in Ethereum. Just you still have to have, for example, multi-sig wallets are pretty common, I would say, when you have multiple people signing a transaction and then it executes. In Ethereum, for this, you have to have at least one account that is used to sign the multi-sig envelope, and then it gets unpacked further down the road by a smart contract. And it is unnecessary because on the level, if you look at Ethereum data structures, you would see that the accounts and the smart contracts share the same data structures pretty much. It's just the EOA don't have the code in them, and we just tried to make it work, and it turns out it wasn't difficult to make it work when we just introduced code into the EOA.
Yeah.
So it opens up a lot of interesting cases. For example, if you are writing an NFT app and you have people who don't care about wallets at all, so you have customers, somebody builds an NFT app and they have customers, and the customers want to just use NFTs, and you don't want them to create wallets, you can use the common wallet that use another scheme of verification for your users, and you would still be fine. The wallet can pay for your users' transactions.
Yeah.
So it's just something that wasn't difficult at all, and it just unifies everything. We just treat the top level, the entry point, to be the originator, the thing that pays for the rest of the chain of calls, and that's it. Otherwise, it's pretty similar to an EOA.
Cool. So I guess in my mind, that kind of opens the door to just other aspects of like account abstraction generally. So what other features would this be able to support outside of this? Like, is there a plan to look at like the different EIPs, like 3084 and a couple of others? And I was just wondering, from a custom smart contract wallet in the future, are there any other features or any other wallets that kind of stand out to you that you would be looking at or like thinking of to integrate with?
Do you mean
It's okay if they're none. Yeah.
Do you mean like MetaMask or things like that?
Well, no. There are a lot of people building.
The wallet contracts.
Yeah, the wallet contracts. Yeah.
Oh yeah, one of the things that comes to mind is because we actually our support for enshrined tokens is, I think it is even in this Ethereum upcoming standard, right?
Yeah.
So what you showed on the Ethereum plan, they also plan to do enshrined token support the same way we do right now.
Yeah.
So I think the idea is just in the air, and they have a desire to do what we did. It's going to take more like breaking changes. So dealing with enshrined tokens, where you store the tokens natively on the wallet instead of the ERC20, is one of the features that we kind of wanted to support and had to support to some degree. And for operating with these tokens, it's very convenient that you can code the interface to your wallet for dealing with sending and receiving these custom tokens.
Right.
And not having to update the static interface of EOAs that you have to have. So it's just simpler to support and move forward. If the users want to upgrade their wallet, they can do so. They just upgrade the contract, move the money to another contract.
Yeah.
That's
Yeah, but definitely a far better UX than what we've experienced now, and hopefully leads to like private key leaks and all these things, which like a lot of people have gotten wrecked because of that. So yeah. All right. Moving on from EOAs and wallets, essentially, I want to move into like contract deployment and some of the differences there that we kind of see. Now, they're kind of connected to the last point, But essentially, what happens is that there's two ways for you to be able to deploy a contract. One is internal, the other is external. Um, Internal is where you like deposit a value to a particular address, and that essentially used for. No, external is the one that you deposit value to a specific address, and when it's created, the value is then spent for that particular aspect of creation. But then beyond that, we also have internal deployment that kind of bundles our contract creation with the message.value. So the value that's like included in that particular transaction is what is used to be able to do that. But that always comes from a smart contract. But also Create 2 is also supported. So do you want to talk us through some of the design decisions when you're looking at like when this was being considered generally, especially with the aspect of like creating, being able to send value to a particular address? Yeah.
Yeah, originally we didn't want to create contrafactual accounts, which is what another word
Mhm.
for
Yeah.
when you send the tokens to the account, and then you can deploy the wallet code to that address. But then the problem is, so if you can only do deployment through other smart contracts, it isn't easy for the user to control their keys and ownership of their account, because when a new user joins the network, what they would expect is that they go to an exchange, or I don't know, on ramp service or something like that, and they want that on ramp service to deposit some tokens to the address, and then do the deployment completely on their own for the added security and trust. So this means that the interaction with the network should happen ideally fully from the user's perspective, from their own hardware or software wallet, and don't go through other people's devices. So this is why we had to support contrafactual accounts, because of the usability. So this is what we support, yes, right now. The address calculation is a bit different from Ethereum, because our addresses contain shard ID as
Yeah.
a prefix, but otherwise the mechanism is more or less the same. The user stores their public key inside the initialization message, and then they
Yeah.
calculate the address derived from that key. And this is all abstracted behind the libraries. And then they ask the on-ramp service to just deposit the tokens, and then they send deployment and sign messages themselves, which is a good way for
Oh,
creating initial wallets and making sure that the tokens don't leak and you really own what you own.
yeah.
And then there is a second way of deployment, which is also present in Ethereum, which is Create 2 call, which we support. You can, if you want to create contract on the same shard, you can just use the Create 2 call and it will work. But for the usual way people would deploy smart contracts, and this is how you would do it through our current tooling with CLI and Hardhat, you would use the deployment through the wallet, which has a convenient function. You just send the code to your wallet and ask it to deploy the smart contract on a specific shard, and then the wallet takes care of this logic.
Yeah.
Yes, and you spend the money from your wallet. So as soon as you have a wallet, you can just ask it to deploy wherever you want on any shard, and it will just forward the message there for the deployment.
Cool. So I guess the interesting thing that that comes from this is, especially when looking at the Create 2 opcode, that it has to work atomically. So it works only inside of your specific shard that you're dealing with, and not you can't do like a cross shard call to be able to create a contract yet, if I'm not wrong. Yeah, that
You
would be
can. It's just not a Create 2 call. We have
there's
a
not a Create 2
special
call.
type of message which is called the deployment message.
Okay.
So every time you want to communicate between shards, you don't do regular calls. You send messages, and what you do is you send a message to another shard with a type that says it's a deployment message, and you attach the code to that message, and you attach a certain amount of tokens to the message, which you can do because you have a wallet, and then it arrives at the different shard. It deploys, and you can track the execution of that message through following receipts.
Yeah.
As for any other operation, you just follow the receipts in a very similar way to how receipts work in Ethereum right now.
Yeah. Cool. Cool. All right. Pausing again in case anybody has any questions. If not, we're going to move on to. So we've talked about like the native currency or the enshrined tokens. So generally speaking, all accounts can be paid in any number of arbitrary currencies created by the account owner or even other accounts. But we also have a special minter role that is basically a precompile. Sorry, that's a um, uh, typo there. That allows for creation, minting, and withdrawal of currencies. So how does that work in practice, and how is this related to like the enshrined token paradigm?
Yep. So we very quickly realized that we can't really do ERC20 in our network, at least not in a way people would find convenient, because no, I mean ERC20. Sorry, I said EUA. Probably ERC20, of course. So ERC20, we cannot really do them easily, mostly because it's a smart contract, and if you want to, for example, send money to two different recipients on different shards, then you want to pay them in, say, USDT. And you would have to send the message to which USDT smart contract. Either you would have to shard that USDT smart contract to be present on every single which differences? We can probably talk about if you are interested in any particular difference, you can ask. I'll answer. I'll get back to ERC20, and then you can ask any questions. So yes, the problem is that in Ethereum, ERC20 is possible because everything is synchronous, and you can call ERC20 smart contract and expect it to finish before your smart contract finishes. And in our case, it's just not really possible. So you would have to send a message, and you would have to wait while the message arrives back, and the usability of that is just not great, especially if you want the shards to be to shed some load. So you don't want to create bottlenecks, and this type of ERC20 would create a huge bottleneck in the system, because almost all DeFi applications work with some sort of ERC20 token. And this is why we thought a little bit, and I think that there are a few other networks that do this, the enshrined tokens.
Oh, really?
I think where I ended up picking up the idea for the enshrined token support. I just don't remember which network was that. So yes, we decided to go with just in Ethereum. There is one field on the smart contract which says the value of this smart contract is this number of tokens. And we added a map to the smart contract that says this token, this many coins, this token, this many coins, and you can have an arbitrary number of values in the smart contract that represent the balance. And the normal rules for spending apply for your smart contract. So this makes it possible to send a message to another wallet, from one wallet to another wallet, and attach certain number of any type of coins. One coin or multiple coins per message doesn't really matter. The protocol makes sure that you're not sending more than you have, and that this is all consistent.
Right.
So if, for example, you send a message to another shard saying, "Hey, here are your tokens," if that doesn't go through for some reason, they will be returned back to you. So you don't have to handle any type of additional error logic or something like that, which makes it very convenient. And also, you don't have to do multi-step operations. If you are interacting with a DEX, it becomes especially convenient. So a DEX would only hold. Usually, they have the currency pair accounts. It becomes very simple. The currencies are actually present on the DEX accounts. They are not holding it in ERC20. They're just holding it within the smart contract that DEX owns.
Yeah.
And the person just sends a message to the DEX, and it can execute all operations locally and just send back the results to one or multiple people, which makes it very, very convenient. It's a slightly different paradigm from just the bare Ethereum, but I personally think it's more convenient. There is, of course, a question with different governance schemes. So minting tokens is easy. So the way we do this is we allow any smart contract essentially to mint tokens, but the identifier of the token would be the same as the address of the smart contract. So it means that only one smart contract can mint one currency identifier.
Yeah.
And other contracts cannot do that. So this makes it easy to understand what contract issued the currency, and it makes it easy to mint and burn the currencies. You just send the currency essentially back to the original smart contract, and it can burn the currency. There is also an ongoing topic of how to do governance, because some of the more interesting types of tokens can freeze the tokens. So USDT, or I don't remember, USDC, I think, does this as well. So they allow
freezing,
the governance to freeze the account of the user. If, for example, they are like linked to money laundering or something like that. Yes, we also know how to do this with keeping money on users' wallets. So essentially, what the replacement mechanism for that would be that an owner of the token can send a special type of message to the user's wallet to lock the currency, but that would only be handled if the address of the source is the same as the ID of the currency. So they can perform the locking operations, and this type of locking would be available with a special flag. So you would know that this particular ERC20 alternative or token is allowed to freeze the balance. So you will see, and you will be able to see through the flag on that smart contract. And they would have to build it in advance during the deployment, and then they cannot change it.
Yeah. Cool.
So just a little bit of a different scheme, but I think it's better for a sharded system.
Yeah. Cool. All right, moving on then. Let's look at like RPCs generally, right? So RPCs essentially, this is how we communicate with Ethereum and most other L2s. And the nil RPC is loosely modeled after the Ethereum RPC. Generally use the same functions for familiarity, but the underlying layer is very different. So when you're looking at like things like get block by number, and the equivalent like ETH_get block by number, for Ethereum, you're just passing like a string. For nil, you're passing like a shard ID, the block number, and like a full transaction if you want to pull the full transaction. So could you like take us through some of the obvious design decisions around this, and what that compatibility, well, not really compatibility, but the development experience, how the RPC kind of facilitates that,
I think one thing that's worth saying is the philosophy on compatibility. So
Mm-hmm.
general philosophy of our network, I would say, is that we want to be fully backwards compatible on the EVM level.
Mm-hmm.
So if you are just like porting or using the Solidity compiler, the general rule is that the off-the-shelf Solidity compiler should be able to produce binaries that can be run on our network. So the EVM should be the same or very, very, very close to what Ethereum does.
Mm-hmm.
This is because we want to keep the smart contract development experience, because this is what users care about. They care about solidity. They care about the same as much as possible, the same approach to development. The further away you move from the virtual machine and the compiler,
Mm-hmm.
the less sense it makes to keep the compatibility and more sense to relax the requirements in exchange for user experience in other things. So, for example, with many integrations that we are making with RPC providers or block explorers or things like that, they wouldn't mind that much the difference in the API, because they would have to take sharding into account anyway. So keeping one-to-one compatibility is not a goal. So and they would likely talk to us through a library anyway,
Mm-hmm.
either in JavaScript or in Go or in any
Yeah.
other language. So we would likely provide those libraries out of the box, as we
Mm-hmm.
do currently with JavaScript, and they would just use the libraries most of the time. But for people who do talk to the network, we decided to at least keep the more or less the function names and what they should do, and expand on
Consistent.
places. Yes, to just be familiar. And we also kept JSON RPC instead of
Mm-hmm.
using any other protocols,
Mm.
because one we think that it's sufficient more or less for interacting with the RPC, and the second is that it's familiar to people who interact with Ethereum, and it also it proved to be more or less correct with people from devnet. So some of you have built on the RPC, and
Yeah.
it's not very difficult to understand because it's close in design.
Yeah. You kind of know what you're
That's
looking for. Yeah.
yeah, that's what we are after. In many places, however, you need to provide shard ID, and you need to understand that if you want to get a block number, there isn't a single block number, but every shard is ticking towards the future with its own block number.
Mm. Mm.
And this is where you need to, most of the time at least, you need to know about the shard ID. Yes.
Yeah.
Go
Go
ahead.
ahead.
Cool, if I may jump in. So I just want to clarify one thing for me, which was misleading on the slide. So we still have ETH get block by number. So we
Mm-hmm.
didn't change RPC methods. So
Mm-hmm.
we changed, I think, two names where we replaced the word transaction with the word message. But overall, the whole RPC from the methods and the inputs is, I would say, 90% the same. So whoever is used to, using the Ethereum, as Konstantin said, sometimes you just need to add a shard ID or these smaller things. And what I would advise anyone who wants to really dive deep and see what are the differences is to go to the link I shared. So we had this problem when we integrated the hardhat, where on one side we have a hardhat which is fully compatible with Ethereum and expecting and sending the same messages and expecting the responses to be Ethereum compatible. And then you have nil. So our plugin is basically catching these requests, comparing the methods, and if needed, and you will see that it doesn't do that many times, it just prepares the inputs and it adapts the response a bit. So I would say that this link is really cool if you want to dive to see the difference.
Excellent. Yeah, this is really cool. Thanks for sharing. Very, very useful. Cool.
Yeah,
Okay.
that's with regards to the RPC.
Yeah.
It's really
Cool.
not difficult compared to other pieces. Oh, and one
Mm-hmm.
important distinction we are using SSZ serialization that is used almost exclusively. We are using SSZ instead of RLP. So Ethereum uses the newer in quotes and simpler serialization format on the consensus layer, because the consensus layer is newer, but they are still using the RLP serialization in the execution layer. But we use the same serialization. We use SSZ everywhere. But outside of that, I would say underlying data structures are very, very similar. If you were to go, for example, through the code, you would see that we use the same account format, more or less, with the same way to compose it with the data of the smart contract, and more or less the same way to attach it to a block. So you would probably feel it very, very familiar. I would say reading our code and reading the Geth code is quite similar, with the only difference being sharding and a different way to achieve consensus. But the execution side is quite similar.
Cool. Yeah, and that gives us like a good consideration from a dApp developer standpoint to adjust our expectations accordingly. I think the biggest difference I've seen, even when I was reviewing the code, was just the occasional addition of a shard ID that would just help route your transactions to the specific shard that you want to process things. Yeah, cool. All right. So let's look at transaction lifecycle. Yeah, go ahead.
Sorry for jumping in. I'm not sure did you plan to add in some other slide, but what I feel it's also extremely important to point out here is that we also enhance, when you said that you had to use the shard ID, and that's the difference. I think that the big point to explain here is how the contract addresses works and how they're structured.
Oh, right, yeah.
So I'm not sure, are you guys planning to say this a bit later, or?
No, we actually didn't. Yeah, but it's an important thing, yeah. That's a good catch.
Because one of the big issues when we started thinking about the UX was that we realized that not everyone can keep track of all, shard IDs and what contracts are deployed anywhere. And if we let users to start think about that, the whole chaos will happen. So that's why the guys created a really smart way where if you look any address, any contract address, which is deployed on nil, you can always take the first 2 bytes and see on what shard it is deployed. And the underlying protocol also knows to take this into account and reroute the messages wherever needed. So the only time when you really care and when you as a user needs to specify the shard ID is when you're deploying the contract. You can say, I want to deploy on shard 1, I want to deploy on shard 2, and so on. Once you have the address, or if you want to interact with the address, which is on another shard, you can just send the async call, and the protocol itself knows how to reroute it, send async call, execute it, and so on. And we can even go a step further and explain the address itself. So we said that the first 2 bytes are the shard ID, but then comes the question how we construct everything else. So the other 2 params which goes into account is the contract bytecode. We use the contract bytecode to have the unique address. But then the next question is, what if I want to deploy the same 2 contracts with the same bytecode or the same shard? And that's why we added a 3rd param, which is salt. So basically, you as a user, you have the shard ID, you have the bytecode, and you have the random salt. And that's how you can create as many contracts, same contracts deployed.
Yeah, that's an important clarification. I think we kind of missed that because, again, we didn't even know how long this is going to take. As you could see, this is probably, we're not going to finish our presentation, but yeah, that was a very, very important clarification. In terms of just
same is true. Same is true. There's an upcoming change to use the same method for receipts and message IDs. So whenever you receive back,
so they're going to be prefixed by the shard ID.
Yes, for the same reason. Right now, if you're interacting through the CLI and you want to get the message receipt, we have this trick with the address, but the receipts don't contain the ID. So if you were to do it manually through the CLI, you would need to specify the shard. But we are adding the same thing right now.
And
Okay.
once they add this, the UX is kind of almost the same as with other Ethereum networks, where the whole goal of what we are trying to achieve, like in NIL, is to make the UX as good as possible. And by doing this, the users don't need to care that much about shards. They care about the dApp and writing their own dApp. The protocol handles a lot of this heavy lifting. And
yeah, that makes sense. That makes sense. Okay, so from a transaction standpoint, this is what the life cycle looks like, and we could talk through this and like try to figure out, or well, not really try to figure out, but like discuss what the stages are here. There's one that is here that's not technically supposed to be here, but I left it there for consideration. But the way that like transactions kind of go through the whole system is you have a transaction submitted by a user or a message. And the transaction is sent to the mempool of an execution shard. It's picked up by a collator, it's bundled, and it's batched essentially. It's then executed, so like the state transitions at that point, and then that block essentially passes local consensus. Now, step 6 isn't necessarily dependent on any of these things. That's like works independently. So, but there's a ZKP network that fetches blocks for that particular shard. And again, the block with the transaction is sent to storage and the transaction reaches soft finality. And like finally, the ZKP and the block are sent to the consensus shard or the main shard, and that produces like a master ZKP. So this is like a general point of like how transactions are being routed through the system. But I wanted to pick on the 0.6 there and like have that be the jump off point of looking at, okay, what does consensus look like inside of a single execution shard, and how does that relate to proof generation essentially, and what role does a proven network play inside of that whole architecture? And that might be the last question honestly we have for today, but yeah.
I think a good mental model of how to think about execution in general in NIL is to imagine that you're dealing with many small Ethereums, and for the purpose of transaction execution, you're likely just sending a transaction directly to a smaller network, and it runs pretty much the same stages as I would say Ethereum would run in terms of like handling a transaction. It's just at the end the transaction can send messages, and for that there is a protocol of relaying messages reliably between shards, which is a different story. But it is this protocol acts almost as if it just takes the message out of one shard and submits it to the input of another shard in the front, almost with just with guarantees. So it bypasses the mempool. But otherwise, you're dealing with many small Ethereums. But ZKP happens outside of this normal transaction executions. So once in a while, there is a network, just a number of computers that listen and replay transactions from the network, and their goal is to re-execute the transactions, but with proving in mind. So they re-execute transaction and produce the execution trace, which is every branch that the code is taking is getting recorded, and then it's like turned into a set of polynomial equations folded, and the ZK proofs are used to produce one value, which confirms that the execution is correct. This is a CPU intensive task. So it's executed on the outside of the network. So normal execution is not blocked by it in any way. So normal execution would run multiple blocks, and once in a while the network would pick up these blocks and prove them in parallel. So these blocks would be distributed across computers, would be individually proven. Then the proof for these blocks would be stitched together into one. So many independent proofs of these blocks would be stitched, and you would have one proof that says that from this block to this block, this proof guarantees that things were correct. And then this proof would be aggregated. I wouldn't go into the technical details of proof aggregation because it's a slightly different topic, and I'm just afraid to lose people.
You don't want to go into recursion. Does it have
Um,
to do with recursion and all those things?
I
Anyway,
don't know if we can really talk about recursion, not because it's a prohibited topic, but because it's difficult.
yeah.
To
Anyway.
be honest with you, I'm not a cryptographer, so it's not like I personally, and I understand the network part pretty well, but
Yeah.
recursion is something that our cryptography team knows very well. So
Because it proves the Holy Grail.
I understand the general idea, but that's difficult.
Yeah.
So that there is just a way to collect multiple proofs together and stitch them. There are papers that talk about that, with Nova being good example. So there are multiple different ways that people came up to just slice a big chunky proof into smaller parts, prove them, and then unite them, chain them together to get proof for a bigger computation.
Right.
This is what we're doing, and we are recording this proof into our main shard, and this is needed for essentially proving the proof later. So we are doing this so that the proof that we get, that we send to Ethereum, is taking from the aggregated proofs of all shards. So we need to verify the proof on the main shard, where we run a special smart contract for verification. Then if we prove the correctness of the main shard at this point, we can then send that proof to Ethereum, and we don't need to send a lengthy set of proofs from all shards. We can just aggregate them into one on the main shard, and then send one succinct witness
for like DA. Okay, cool. Yeah, so again, loads there we could like unpack and talk about, but we have 1 minute left. So
I think we can probably spend some time if you want. I don't think we're that limited by time, but it would be good if you can ask.
Okay. Yeah,
if you all can ask questions.
Yeah, if people have questions or thoughts or comments, please feel free to ask. Or you could just tell us, was this session useful, or you're like, nah, this was a total waste of my time.
It was great, actually. Thank you, Konstantin. Yeah, what's very clear explanations.
Yeah.
Thanks for that. There's a question on how shards communicate with each other. Yes,
you want me to jump over to that slide?
Yes, you can. You can jump over to that slide.
Yeah. This one? Yeah.
Yes. So there are two parts to this answer. So sending network packets themselves is not difficult. So you can get a network packet from A to B without big problems. So that never was a problem. So delivering, we use, for the network layer, we use libp2p in the same way as Ethereum does it. And the choice for libp2p was pragmatic. Of course, we have a lot of things to invent, and network layer is not one of them. And we don't, we really don't want to be inventing things that shouldn't be invented, because the ZKPs are enough of an invention, and sharding is enough for us to keep ourselves busy and keep the fun up. So yes, network layer is libp2p. You can broadcast things through libp2p, and you can do point-to-point requests. So if one shard wants to send, well, it produces the block. In every block, there is an outgoing message section. So if other shards can listen to that block when it is produced, they can just get the messages that are destined to them. The problem is how can we guarantee the delivery? And this is where it's difficult. So imagine if one shard didn't receive the notification, or they just went back and they want to trick the rest of the network to just they just don't grab the message for some reason. We need a way to reliably slash them for not performing message passing correctly. And to do that, the main shard serves as a clock. So if you are familiar with databases, there is a concept of vector clock. And what main shard does is it includes the hashes of all current tips of every shard. So if you look at the hash of the main shard block, it contains references to shards. So if you have a reference, you can say that these shards must have received certain number of prior messages at this point, and they cannot execute further messages without processing the prior messages. This guarantee is given by inclusion of the individual clocks. So you are essentially force synchronizing the clocks of individual shards once every like couple seconds. Shards may delay to a certain degree not the message delivery, but they cannot deliver out of order or skip message delivery, so that they would have to pick up the messages within a bounded amount of time. There is a way to ensure the ordering of messages, and to explain how the ordering is performed, you probably need to understand the concept of the vector clock. But essentially, if you are having the time synchronization once every couple seconds, you can say that this master chain block is preceded by this master chain block, and this the messages emitted by this previous block referenced from this point, they should be delivered earlier, and these messages should be delivered later. So we can enforce the ordering, and this is how we avoid a certain type of MEV attacks. So, for example, the validator is not free in how it orders the messages that are sent internally. You have a how is called a strict partial order between messages. So there are ways to reorder within a very, very small window, but it's not enough in general to perform any interesting MEV attacks. So yes, it all boils down to this main shard idea, which is a forced clock synchronization. The delivery happens, yes.
No, after you finish, I want to add. I didn't want to interrupt you.
Yes. So delivery happens either by one shard listening the production of the blocks on other shards, or by explicit requests. So if a shard knows that it needs to fetch the certain messages from other places which it didn't handle yet, so it must go and it must check and it must include them. Otherwise, down the line, it will get slashed. And of course, the ZKP would not converge, so the network would be rolled back if the shard misbehaves in message delivery.
Yeah, I want to jump in because this was a really good explanation on a really low level. So I just want to conclude, if anyone on this call is just a dApp developer and you want to know how all of this works on the really high level without going into clocks, main shard, and so on. So basically, you need to know two things. Currently, if you want to send a message from one shard to another, we have our pre-compiled, which has the async calls. So you just set the destination address, set the message or what you want to do, and everything will be done like under the protocol. Also, the next big question, which we get always, is how fast it is. And the only right answer that I can give you right now is 2 blocks, because you need to insert the block on the source, then you need to insert the block on destination. And basically, if you want to create the full mathematical formula, for the whole async call, it will be like you insert the block on one shard, you do this really quick transfer that Kostya explained, then you insert the block on another, and vice versa. And that kind of, without going into details, this is like from the dApp smart contract side, this is the only thing you need to know. And now comes the question, how can I design the dApps? And this is like a really huge question for all of us. So the one approach that we currently give out is classic callbacks. So you can send something and then have a callback, what will happen when it gets back. And the team is actively working on creating more patterns, creating the UX better, and so on.
Yeah. Cool. Dope, dope, dope. All right, everyone. Well,
Will we give sneak peeks?
sneak peeks of what?
Yes, that there's going to be a release soon.
Oh, right. Yeah. Go ahead. Go ahead. Yeah. By all means. By all means.
Yes,
Let me
so
actually- yeah.
we are just we just want to give a little bit of a
Alpha,
teaser. I think
alpha.
yes, I think it's going to be within a couple of days.
Yeah.
So what's coming is that first we have now a better model of withdrawing the fees, as I've written in the chat a couple of times. So the new model, in the new model, you would have separate fields for the value that you want to transfer and for the value that you want to pay your fees with. And that value is going to be propagated down the chain of messages. And this will make it very easy to reason about how you pay for the chain of calls. Currently, it's difficult for no good reason. We just didn't have time back then to implement this idea. And now we have it implemented and it works decently well. So we already updated the core code base, the library code base, and we are going to release it soon-ish. The CLI has got many improvements with the ability to read the raw blocks, and you will be able to just dissect the block content from the convenience of your own laptop. Where else? We also implemented, and we are now in the process of implementing ETH call. So one of the things that we want to have is for you to be able to estimate how much gas you would spend for the many asynchronous calls. So in Ethereum, you can estimate the gas, but it's easy because you can do one operation, and that operation completes, and you get the estimation. In our network, because it's asynchronous, you can perform multiple calls back and forth, which happen in different blocks, and they want to give you the same level of convenience. So you'll be able to send a message, essentially, and it will track the execution in a dry run mode on an archive node without applying, and you would get back the result of all this chain of calls. So in the new version, we don't yet have the whole chain of calls, but you would still be able to call individual smart contracts, and you will be able to persist the state in between the calls. So you can deploy a contract in a dry run mode, in a special dry run mode. So you, from the CLI, just deploy a contract, call it, and it would not modify the state in production. It would not charge you anything, but it will simulate. And it will save your state locally, and it's a very convenient quality of life addition. So I think Aragon has this to some degree.
Yeah.
But we are making this, I think, a lot better in the final design. So this is a way for you to estimate the gas cost of async messages, and will give you better way to time the execution and set the correct value for gas payments. Did I miss anything? I think that there was something else pretty significant.
No, I think it was the There were two things. Yeah, it was the fee, and then mm, yeah, I can't remember.
And CLI
You
changes.
cannot reveal everything.
Yeah.
Also, finally, one of the big things that we want you, and this is what I want to ask of all of you, is try writing smart contracts, especially with async calls, because right now it's still possible to change a lot of the things about the network, and this is one of the biggest things for us at this point to get feedback on, because this experience of how people use Solidity to send async messages and handle callbacks, it is important for dev developers in particular. So there are things that I don't think you realize that we can really make this better by introducing changes into the protocol. For one example that I can give is that we are thinking about reliable callbacks. So whenever you send an outgoing message and it executes a chain, something that then executes a chain of subsequent calls, and then you would reliably always get a result, even if something down the line on another chain of calls errors out. You would always get a reply. So it's one of the features that it's possible to do on the protocol level, and we have to work it into the protocol. So, but it's possible to change a lot of things about the protocol right now. So give it a shot, and let us know what you think.
Cool. In respect of people's time, I'm going to pause our event today at this point, and just allow people to continue on with their day. But we really do appreciate everybody coming out today and for just being a part of this whole process and giving us an audience and talking about this. But yeah, I'll end just with a reminder. Please write contracts and write async contracts and get back to us about your experience. But for now, thank you very much. Goodbye, everyone.
Thank you.
Thanks for coming here, and we
Thank
will
you.